On average, a star goes supernova once every 50 years in a galaxy the size of the Milky Way. But why and how does this happen, and what does it mean for the development of the universe? Welcome to the Daily Galactic. Today we're talking about the deaths of stars and the incredible remnants they leave behind. We've known about supernovas for a very long time, with the first being recorded in 185 AD. Catalogued as RCW 86, ancient Chinese astronomers noticed a guest star that stayed in the sky for 8 whole months. However, it wasn't until the 1930s that the term supernova was used. The vast majority of supernovas that we observe actually happen in other galaxies outside of the Milky Way, and they're so bright that they can easily outshine a galaxy. In the Milky Way, thick clouds of gas and dust usually block the visible light erupting from these explosions, making it very difficult for us to see. Modern-day astronomers have categorized supernovas into 2 main ways, Type 1 and Type 2. Firstly, we'll take a look at Type 2. They're the more well-known and the more exciting type of supernova. For a star to explode as a Type 2 supernova, it must be several times more massive than the Sun. The best estimates run from around 8 to 15 solar masses. To understand what happens in a supernova, we must first look at what a star is and what processes happen within. Stars are giant celestial bodies that are primarily made of hydrogen and helium. They produce light and vast amount of heat from the nuclear factories that reside in their cores. Inside these cores, the temperature and pressure conditions are so strong and powerful that the thermonuclear fusion of hydrogen into helium can happen. This reaction provides stars with the incredible amounts of energy they need to survive. Throughout the millions and billions of years that stars live for, they slowly burn through their hydrogen fuel and then their helium fuel. When the fuel of smaller stars like our Sun slowly diminishes, its core contracts and heats up, warming the outer layers and causing them to expand until the star becomes a red giant. The core will then become hot enough and the pressure will have built up to enable the helium to fuse into carbon. When the helium runs out, the core will expand and cool, being made mostly of carbon and oxygen. The upper layers of the star then expand and eject material off into space, forming what's known as planetary nebulas. They're some of the most beautiful cosmic structures we've observed, and at the centre is an incredibly dense white dwarf star. But we can talk more about these another time. For more massive stars, things go a bit differently, and they produce some of the biggest explosions that we know of. When their cores run out of hydrogen, helium fuses to carbon, just like smaller stars. However, their mass and immense pressure means that the carbon can fuse to heavier elements. Oxygen, neon, silicon, magnesium, and sulfur are just a few elements that are created at the center of massive stars. This process is called stellar nucleosynthesis and keeps occurring until iron is formed. Once the core has turned to iron, the star has no more fuel left to burn. At this point, the gravity of the star is too immense and begins to collapse in on itself, causing the iron core to heat up. In the core, at the smallest molecular scale, protons and electrons are packed so tightly under the intense pressure that they merge to form neutrons. An incredible change in the structure of the core occurs when this happens. A core of a star this size can be a similar size to the Earth, and in an instant transforms into a neutron core with a radius of only about 10 kilometers. The space that the core used to take up must then be filled, and the pressure and gravity of the star makes the outer layers fall inward to the neutron core, crushing it further. The core heats up, rapidly reaching billions of degrees, and finally, it goes supernova. The powerful shockwave that blasts out from this explosion can trigger star formation in the surrounding molecular clouds as it pushes hot gas and dust into each other. What's left over from this cataclysmic event? Well, for the medium-sized stars, a neutron star is left behind. Usually they're only about the size of a city, but they pack a mass of about 1.4 times that of the Sun. For the most massive of stars, a mysterious black hole is left in its wake, a region of space-time that has such a strong gravitational impact on its surroundings that not even light can escape from it. For Type 1 supernova, it must take place in a binary star system, where two stars orbit around the same point. It's generally believed that one of these stars must be a carbon-oxygen white dwarf, left over from a Sun-like star that's reached the final stages of its life. It orbits with a larger companion star, and as the gas of the larger companion star slowly accumulates onto the surface of the white dwarf, it continues to become more and more compressed. This build-up of extra pressure pushing down on the core leads to a runaway nuclear reaction deep within the star that builds up to a huge cataclysmic supernova. Left over from the biggest explosions found in nature are some of the most beautiful and intricate cosmic structures that have been photographed. Here are some extraordinary images captured by various ground-based and space-based observatories. These are classified as supernova remnants. They're created from the powerful expanding shockwave that shoots out into space. They're made of the ejected material of the dying star and all of the interstellar material that gets swept up and shocked along the way. So why is the study of supernovas so important to our understanding of the universe? Well, they greatly impact the ecology of the Milky Way, warming up the interstellar medium, which is the gas and dust between stars, providing vast amounts of energy and clumping the interstellar medium together to trigger the next generation of star formation. Supernovae are also believed by most astronomers to be the cause of mysterious cosmic rays that commonly blast into Earth. The powerful shockwaves that supernovae create accelerate electrons, protons and ions to near light speed via a process called Fermi acceleration. By rattling back and forth in these shockwaves, they're eventually rocketed out to space and become cosmic rays. In addition to this, they were able to help us prove that we live in an expanding universe. A subtype of supernovas called Type 1a are some of the brightest events in the universe, and all shine with incredibly similar intensity. By observing these supernovae over time, astronomers were able to deduce that all supernovas are moving away from the center of the universe, just like everything else. But most important of all, if supernova remnants didn't exist, then neither would the Earth, or the majority of other planets for that matter. As discussed earlier, in the dying cores of stars, many different heavy elements are created. This means that all the oxygen you breathe, the iron in your blood, the calcium in your bones has all come from the cores of stars.
The surface of the Earth is the shore of the cosmic ocean. On this shore, we've learned most of what we know. Recently, we've waded a little way out, maybe ankle deep, and the water seems inviting. Some part of our being knows this is where we came from. We long to return. And we can't, because the cosmos is also within us. We're made of star stuff. We are a way for the cosmos to know itself.
Thanks for watching. Feel free to comment any questions you have or what videos you'd like to see, and I'll do my best to answer. Leave a like and subscribe for more videos about our amazing cosmos, coming very soon.